You start.
Yeah, I'll start.
Good morning, everyone, and welcome by the first press conference of the day. It's still a little bit early, but we've got the right topic to wake you up and excite you a little bit, because these presenters over here are going to talk to you about lightning hazards and lightning detection networks. With us today are Mr. Colin from the Department of Geophysics and Planetary Sciences of the Tel Aviv University in Israel. We have on the right Oscar van der Velde from the Technical University of Catalonia, Spain, and also Vera Meyer from the German Aerospace Center, DLR Oberpfaffenhofen in Germany. Please go ahead, guys.
Okay, so I'll start. I have two different topics to talk about. And the first one is related to a European project called FLASH, which is funded by the European Union in the 6th framework. And there was partners from 5 different countries, 6 different institutes, from Italy, Greece, Spain, Cyprus, and Israel. And the focus of this project was to use lightning data to better understand flash floods. And flash floods are one of the major natural hazards in the world, but especially in the Mediterranean. To show you some of the results, I'll just look at one example of a flash flood in Catalonia, September 2006, where, well, I should go back. We looked at 23 different case studies of flash floods which occurred around the Mediterranean to see if we could use lightning data to better predict these storms, to better understand the storms, look at relationships between lightning and rainfall. And the lightning network we use is the network called Zaius from the National Observatory of Athens. We can see here a map of the Mediterranean with lightning shown at different times of day. The colors, the different hour of the day, which is shown at the bottom. And I should point out that these data are available free to the public in real time on the website you can see here, the flashproject.org. And one of the ideas of the project was to develop tools that can give very short-term forecasts for the public, to better warn the public and civil emergency management personnel. And this is some of the work, for example, for that flash flood. I showed you the picture of the floods in Catalonia, where we can see the forecast. These circles represent the 80% confidence region, where we have an 80% chance of flash floods in the next few hours. The colors represent the lag time, going from the present out to 2 to 3 hours into the future. As we go out into the future, there's more uncertainty, so the circles get larger in time. And if we these experimental forecasts are also available on our website now. And so if there are some thunderstorms around the Mediterranean today, then this is an automated software which will give us an estimate of the motion of these storms, where they're moving, and the regions which are likely to be impacted by these thunderstorms in the next few hours. Another aspect of the FLASH project was to try to improve weather forecasts of severe rainfall and flooding in the next few days. Nowcasting is normally for the next few hours. Forecasting is using a model for the next few days. And this was done by our partners from Greece. Here on this map you can see the little blue, dark blue area. There's the mouse. With the red circle around it. This shows the forecast for regions which would expect heavy rainfall in the next few hours, and the forecasts go from the next 6 hours to the next 72 hours. But we only show on the map the regions of intense rainfall so that it doesn't become too complicated. And this is also updated every 6 hours and is shown on our website for use for weather forecasters or the public, and obviously this is all free. So part of our research, and my next talk as well, is to show how lightning can be used to study severe weather, track different types of high-impact weather which impact the public. There have been relationships found between tornado occurrence and lightning. As I mentioned, the flash flood's been working, hailstorms, and even hurricanes. And so with that, maybe, I don't know if we want to stop for questions or just go on to the next topic. Let's go to the next one then. Can you open the other file?
Sure.
So that was a short explanation about this FLASH project, which is coming to an end this year. It will be ending in the summer of 2010. The next topic, which is it's related to what I just presented about lightning being used for severe weather, but this is not related to the FLASH project, is related to lightning activity in hurricanes. We know that hurricanes are huge damaging storms which can cause both economic damage as well as taking lives. Depending on where they hit, they can cause tens or hundreds of thousands of deaths and losses. And until recently, we've been quite blind to what's happening within hurricanes, because hurricanes start and form and most of their lifetime is over the oceans where nobody lives. We can see in this map the blue regions where hurricanes form around the globe in the different basins. We need warm water for hurricanes to form, and we also need the effect of Coriolis force to give the storms a spin. And so we don't see many hurricanes on the actual equator, but as we go north and south, we see them forming in the northern hemisphere and the southern hemisphere, obviously only in the summer months when the water is warm enough. And the red arrows show the actual trajectories, the way they move, normally with the trade winds from the east to the west, where the numbers show the average number of hurricanes every year, and in the brackets we see the percentage that occur in that region. So most of the hurricanes actually are in the West Pacific. About nearly 40% of all the hurricanes there, they call them typhoons. In Indian Ocean, they call them tropical cyclones. In the Atlantic and East Pacific, hurricanes, but they're all the same animal. So as I mentioned, most people only have studied hurricanes when they come close to the shore, when they have an impact on the human population, and when our detection networks, whether they're radar or lightning, can detect these storms. But recently now what we've done is we've started to analyze from 2005 to 2007, we analyzed 58 hurricanes of category 4 and 5, the most intense hurricanes, to see whether they have lightning activity in them and how the lightning changes over the lifetime of the storm. And this has now become possible because we have a new global lightning network called the Worldwide Lightning Location Network, or WLLN, and this can also be seen in real time, the lightning around the globe at www.lln.net. The little blue dots here on the map are the lightning detected by the ground stations placed above the clouds in white. The stations are shown by the little red stars in the circles at different locations, including our station here in Israel, in Tel Aviv. Now, lightning propagates from its source to the observer by reflections off the ionosphere and the Earth's surface. It bounces off the upper atmosphere and the surface, and therefore can travel up to thousands of kilometers before it decays into the background noise. So even from our station, for example, in Israel, we can detect lightning from the middle of Africa, from all over Europe. And by using a few different stations, you can actually triangulate and get the location of the lightning. This network basically uses the difference in the time of arrival of the electromagnetic pulse at every station. There's a very small difference in the time that it will take for lightning to reach Tel Aviv and then Portugal and South Africa. And this difference in the time of arrival can be used to locate where the lightning is to an accuracy of about 10 kilometers. Now, we're only picking up the most intense lightning because of this distance that the lightning has to go. The weaker lightning isn't detected very well, but still, as we can see on this map, we see where the thunderstorms are located, and we get a relative indication of how much lightning is occurring in these thunderstorms. So we decided to look at some hurricanes. For example, here's Hurricane Katrina, and then here we can see the lightning activity in Hurricane Katrina in 2005. And we see very nicely the structure of the hurricane with the rain bands and even the eye wall. And this is going out to 800 kilometers from the center. The scale on the X and the Y axis from the center of the hurricane is plus minus 800 kilometers. So these are huge storms and lots of lightning activity in them. So for the 58 storms, we simply counted the lightning activity within the storms, and to see how the lightning changes as the pressure or the wind speed in the storms change. So here's an example from Hurricane Dennis. We can see the trajectory of the Hurricane Dennis, which came into the United States in 2005, July 2005. The top left, we see the pressure at the center of the hurricane. The lower the pressure, the more intense the storm. And this we can see in the bottom, the inverse relation is the wind speed, which gets up to a maximum of 140 knots. This is in knots, the units, which is a Category 5 hurricane. And this hurricane had two different peaks. We see it decayed and then it intensified once again. And if we look at the lightning activity in red here, we see that we have a very similar pattern, but there's a lag between them. And that the lightning activity also has these two peaks, but the peak in the lightning activity occurs 1 day before the peak in the wind speeds. And we found this occurred for more than 70% of the hurricanes we looked at, that the lightning activity peaks 1 day before the maximum intensity of the hurricanes, and therefore we can maybe use lightning activity from these global networks now to study the intensification of thunderstorms and give a short-term prediction of when the hurricanes may peak. If we look at the correlation between these two curves, without any lag, it's 0.74. But if we shift the red curve 1 day, it goes up to 0.92. So highly significant, the relationship between the lightning and the wind speed. And here, just last slide for the 58 hurricanes with the names we can see on the bottom here. We can see the statistical correlation coefficient, the linear correlation coefficient between the lightning activity and the wind speeds when we shift them to the maximum agreement. So all of these storms show very high significance when we shift them. They do have different lags for different storms, and this is a topic that we're studying now, but as I mentioned, 70% of these storms we looked at, the lightning peaks before the maximum intensity of the hurricanes. So with that, I'll finish. Okay, you want to go next?
Okay, I will start. So the next topic considers the other forms of lightning which occur not in the thunderstorm itself or under it, but above it. In this picture, you can see several types. We have that. Well, I have this one also. Several types of lightning that shoots either out of the cloud, like this one. This is a gigantic jet. This is a blue jet, so it comes from the top of the thunderstorm. And sprites. Sprites are discharges that actually initiate not from the top of the storm, but in middle atmosphere, in the mesosphere. And an ELF is you could express it as some shock wave that results from the pulse of a very intense lightning flash. So these are very exotic kinds of lightning, and they offer us unique possibilities, especially if, for example, you have a red sprite. They are high-altitude electrical streamer discharges. So they develop at a pressure at altitudes where the pressure is very low, and this you cannot really do in your laboratory. So for streamer physics, it is very interesting to study these discharges. And also, there is a relation between normal lightning flashes, and this relation has to be understood. So there is a strong lightning flash in the cloud, discharging a lot of, discharging the cloud by removing the charge to the ground. And then this creates this high electric field at these altitudes, and then these streamers develop. So what I said was, so you have actually a very good possibility to study this if you like streamers and electric phenomena. So it's a big natural laboratory. They also have their influence on chemistry in the middle atmosphere, which could be of global importance. And it's important to know what is actually a streamer doing. And there are, for example, the hot lightning channels and cooled streamer channels, and their interaction and the way it is all caused by electric fields and also the possible involvement of energetic particles, which are observed even from space as terrestrial gamma ray flashes. These are very important to investigate. And of this I have, we currently in Europe use these kind of tools. This is a high-speed camera, which can take, well, hundreds of thousands frames per second, but in order to observe sprites, you need a reasonable field of view. So then we can use only lower speeds of around 10,000 frames per second. And what you then see, if you resolve this in high time resolution, is, I'm sorry, I have to look up a little bit in this directory, is, for example, okay, I hope it's visible on the screen. Well, we usually tend to zap a little bit. And there we go. I repeat it and then slower. So this is a sprite which occurs at a... there we go. So you have a streamer starting from some point, and you then have a downward development and then upward development. And you can even see that the sprites can interact with each other. Because here's an ancient, well, previously formed column, and this sprite is obviously attracted by it. So there are very surprising mechanisms in these streamer discharges. So let's stop this. Back. So with this camera, actually, even the lightning is still a mystery, because the lightning discharges seen by this camera, they can be also very spectacular. For example, we managed to record in Spain. So these are our first recordings of last year. This was actually like almost the second lightning flash we caught. So it will start at the left with some discharge here. And it seems to trigger all of a sudden, hop, a lightning channel growing upwards from the this is probably, there is some kind of an antenna on the ground, and then a whole series of discharges follows. And you see many of these are very short lasting pulses. So here it's probably some channels, and then you have reactions in those channels that transfer all the charge in the cloud to the ground. And another example of a lightning flash. And actually what we're trying to do in Spain is to see if simultaneous with these lightning flashes, if high energy emissions like X-rays and gamma rays are detected, and to which process they are related. As you see, now you see after the big discharge, you see some additional flashes, like if we zap a little bit, but this is risky because... So that's a return stroke, the bright flash, and these are leaders coming down from the cloud. So we want to know what causes the high energy radiation. We also use electric field measurements to go along, but it is very tricky to record the high energy radiation because it doesn't propagate very deep into the atmosphere at these pressure levels. It's much easier at high altitudes, and this is why it's seen better from space. But even then, you need to be very lucky. And to get back to the topic of discharges above the clouds, let's go here. So we had actually many campaigns already in Europe called Eurosprite, in which several cameras are installed to observe the region of Spain and France and see these discharges. But only a few types of discharges have been seen so far. These are the ELVs, the sprites and the halos, which surround sprites or sometimes occur alone, but never the jets. So there is a mystery as to why don't jets appear so often. So what in a thunderstorm is necessary to create upward discharges from the cloud? So we haven't seen this, but then all of a sudden in December, from a winter thunderstorm, which is very surprising, and this is also the first time in Europe that we have a gigantic jet, as this is called, which rises from the cloud, shoots up all the way to the ionosphere. This is 90 kilometers high. And in this case, it was even surrounded by a sprite. So this is still, during so many years of observations, you can still detect very strange events that puts us for surprises. This was, for example, you can measure the polarity of the discharge. There have been previous gigantic jets of negative polarity, but this is a positive one. So it's very strange. And this is also, as you can see, not observed by the Eurosprite, not by professionals, but by the Italian Meteor and TLE network of amateur observers. And so this field of science is great because it is one of the few fields in which amateur observers can contribute to advancements. So thank you. That was my part. I put. We go back now.
You need the first slide?
Yeah, wait. I can do it.
So
full screen. Wait a second.
So good morning. We have seen that thunderstorms and lightnings have an amazing appearance, but they are really dangerous for people at the ground. And I will talk about the European Lightning Location Network LINET and its application for thunderstorm nowcasting. And to summarize, the advantage of lightning data for thunderstorm nowcasting, I can say that they reveal the actually active regions of a thunderstorm in real time, which is not possible with radar data and satellite data. And they allow a close storm tracking and the monitoring with high update cycles of thunderstorm evolution and development. And they provide forecasters and users with the information about severe weather conditions, and they can provide cell nowcasts. And finally, they are still an active field of research with very interesting and promising results. So here you can see a 3D visualization of LINET data of a normal thunderstorm, where you can see LINET can resolve lightning location in 3 dimensions. So you can see here is the cloud lightning, which happens in the cloud and which do not develop a channel to the ground. And here you can see the cloud-to-ground lightning, where channels are developed and connected to the ground. And here you can see the appearance of a severe storm, also recorded by LINET, and you can see a clear difference between both discharge characteristics. And recently at the DLR, a lightning cell tracker has been developed, which uses LINET data to identify and track lightning cells or thunderstorms based on lightning data. And here you can see a lightning frequency map with a current thunderstorm detected by lightning data. And you can see the cell track, and here it approaches Munich airport and endangers the area there. As the cell is tracked through space and time, cell parameters are recorded and then investigated. And based on the cell history, forecasts are done which predict the cell position and the cell behavior for the next 20 minutes, so that the area there can be warned. And the advantage of lightning data is that they resolve in real time the actual active regions of the storm in high spatial and temporal resolution. And this is an important information which could probably help pilots to avoid risky regions, storm regions. As you can see here, where you can see that the thunderstorms are resolved by the lightning data, and the pilots try to avoid the active regions here. And this is a slide with the very recent results of current research. It shows the correlation of lightning frequency versus cell area. And as you can see, there is a clear and strong correlation between those two cell parameters. And you can also see that there is an obvious break in this discharge behavior at a cell area of 160 square kilometers. And it appears that short-living cells, that they develop within this region here, various long-living cells with higher discharge frequencies, they develop into the second region here. And so based on these results, it seems really likely that you can connect life cycle and lifetime with discharge characteristics. And this could be used to predict the cell trend of a currently identified active thunderstorm. And this would help forecasters and providers to warn and to do their cell predictions. So this is the end of my talk. So,
okay.
Thank you.
Thank you, all the three of you, for your interesting presentations. We have about 15 minutes now for some questions and answering.
I have a question for Colin Price. I'm Liz Callagher from Environmental Research Web. You're talking about forecasting the maximum wind speed in hurricanes. Could you talk a bit about how that's being done at the moment and what the advantage is of knowing when the storm will peak?
I don't think it's being done at the moment. Most of the research at the moment is when the hurricanes are coming close to landfall. And then most of the predictions are done on the track of the storm, which is done fairly well, actually, since the actual movement of hurricanes is determined by the large-scale environment, the wind patterns with the high-pressure cells, and the flow of the trade winds. The intensity of the storm is less well predicted, and this is attempted to be done by models, computer models. But all models depend on certain initial conditions, and the initial conditions have to be taken from either flights from aircraft over the ocean, satellite observations, and until now there's a big discrepancy between model predictions of storm intensity and the forecast for the next day. So at the moment not much is being done really, and what is done, there's a discrepancy between different models. And this is one of the big questions in hurricane forecasting is the intensification. When is it going to reach its peak? When is it going to decay? Will it reach its peak over the ocean before it hits the land? So lightning may be an additional tool that can be used before it even gets close to the land.
Dagmar Röhrlich for the German radio station Deutschlandfunk. Why is there this connection between lightning and this one-day bias between lightning maximum and the maximum of the storm?
We don't know. This is a topic for a research we're continuing now, the research trying to use models to try to understand this. There is some studies which have been done also from MIT and from other places back even more than 10 years ago, which show that in order to organize the horizontal organization of hurricanes, you need to have very intense convective storms. And the puzzle again is that lightning is related to the vertical movement of wind and convection, and the hurricane winds is the horizontal winds, the maximum. And it turns out that you need these convective plumes or towers within the hurricane to organize the hurricane somehow. How that's actually done, we're not really certain. But it's noticed that in hurricanes which are reaching their peak, you develop these what they call hot towers, which are these towers of convection which go all the way through the atmosphere, and these have the lightning in them. But the actual mechanism of how we connect the vertical convection to the horizontal wind is still a bit of a mystery. But these previous studies have shown that there is a lag time between the convective cloud development and the peak winds of about 1 day. So it matches previous studies.
Are there any more questions? Then I think this concludes this press conference. Well, thank you everyone for your time and attention.
Thank you.
Thank you.
Thank you.